All right, everybody, let's go ahead and get started again. So next up, we've got Pedro Fernandez from Huawei. He's going to talk to us about the 48-volt implementation for their PowerShelf. Go ahead.
Right. Thank you very much. Good morning. Thank you for joining us for this talk. We'd like to talk to you a little bit about the 48-volt standard, kind of in a practical approach. We went through an exercise of saying, well, what would this product look like, and developed a product. And we'd like to share some of the challenges, some of the things we learned as we worked on this product. And quickly, just talk a little introduction to Huawei. If you don't know Huawei, Huawei's a very large communication company. We have products in all sorts of communication markets, specifically our network energy group. We're largest energy product provider in the world. 2 million telecom systems, over 800 large data centers worldwide, huge amount of solar plants. Huawei's very experienced in power, and we're very happy to join the OCP, be part of this initiative, this open collaboration to develop, the next generation data center. So first, I'm going to spend a few minutes talking about why people are considering 48 volt. That's obvious to some people, so I'll try to go through these relatively quickly, but it's also important that we understand kind of the basics of why we got here. So short answers are, it's overall more efficient, right? And these are the contents. And then we're going to review data center efficiency, and then what our open rack design looked like. So why 48 volts? So OCP and data centers in general traditionally supported 12 volt racks. Obviously, there's a lot of 12 volt products out there. It's been successful, so why would we change? And basic, simple answers are power density, efficiency, both at the rack and a site level, and then the economy of scale. So talk a little bit about each one of them regarding the power density. So as the density of the equipment, and of course this is all based on equipment. If you're not powering anything, you don't need a shelf. You don't need a power shelf, right? So as the equipment that you're putting in the racks, that you're packing into these data centers, as it needs more power, it becomes less and less efficient to provide that power in a 12 volt system. And increasing the voltage, going from 12 to 48, obviously that's 4 times more voltage, so it's a quarter of the current. That trickles down to a lot of improvements. You have a lot less copper, a lot less copper that's in the way of airflows and other things. And it's more efficient, right? You just lose less power to heat, right? And when you generate heat in your racks, you've got to have air conditioning to take the heat out of the building. So it just improves efficiencies throughout. And generally, our analysis, we think that once you're getting around the 15 kilowatt range for your rack, the 12 volt system just starts making sense, right? You're just putting so much time and effort and space into that device that it just doesn't make sense. Okay, so let's say we agree that 12 volt is limited, right? So why pick 48, right? Why not 70 volts or 100 volts? Why not 300 volts? Well, the main reason for that is what's considered low voltage, right? So there's a voltage at which, if you're beneath this voltage, you have far fewer safety considerations that you have to worry about, because simply it's safer, right? You can actually touch it. And low voltage is recognized by different organizations. NEC, NFPA, OCP all have some sort of limit. They all range in the 50 to 60 volt range. And so if really 60 volt is like that magic number, if you start going above 60 volt, if you violate that voltage, then it's no longer considered safe voltage. You have to have an electrician, right? Technicians can handle stuff below 48 volts. Electricians have to handle stuff above the 60 volt range. So that's one of the reasons why you wouldn't just randomly pick 100 volts. 100 volt DC is actually pretty dangerous. And also another very important point, as data centers grew, they grew in this world of 12 volts, but the telco industry, which is actually Huawei's strength, right? We've been a telco provider for years and years. They've always used 40 volts. I mean, that's going back decades. And so there's a wealth of products that already exist, right? You don't have to reinvent the wheel. And so it's logical for the next step from 12 to go to 48. That's just a very logical step. And again, staying below 60 to keep the electricity safe. Okay? Now, just to continue a little bit of the thought process on the 48. Okay, so telco uses 48, but they use negative 48, right? Is that what we're considering here? Well, telco standardized a negative 48 because a lot of the plant, the telecom plant, was outside, right? In the olden days, you had a wire going to your house. I mean, most people still do, but you're not really dependent on it anymore. But there was literally a wire, an analog wire with an analog signal going to your house. And the way corrosion works is it actually moves to the positive side of the terminal, basically. So if you have the wires carrying negative 48 volts, then the cabinet or the framework will take the corrosion hit. And that's preferred in the telco space. In some other space, you might not want your framework to take the hit, like, for example, a bridge. You don't want the bridge framework to take the hit. But in telco space, it certainly made sense for the wires to be protected and let the framework take the hit in corrosion. Now, that's not a big deal in the data center world. But the bigger issue that should be considered is the total potential voltage that you might have. Now, part of the OCP standard is you could have a rack and you could have a 48 volt bus bar vertically in the back of it. You could also have a 12 volt bus bar. If you were to standardize on negative 48 volts, you could have a potential of 60 volts between two bus bars, right? And that could violate your low voltage limit. So the standard allows the power supply to be plus or minus 48 volts, but it's more logical to stay with a plus 48 volt system because the 12 volt is plus. It's a positive voltage. And again, corrosion is not a big deal in data centers, so it's not something to worry about. Now, just one note for telco people, you can't just take a negative 48 volt telco shelf and put in a positive 48 volt environment because your grounding internally may not be suitable for that. You probably have to do some sort of modification to make it work. Okay. Another question may come up, and again, this is just a little preface of the 48 volt world, right? Because we came from the, Huawei's comes from the telco world. So, okay, 48 volt, we buy it. That's what we want to use. Where's the 54.5 coming from? Well, that was actually, the standard was 48, but in fact, most systems run at 52.5, 54.5, depending on the kind of batteries. That's actually based on batteries. That's because we float the voltage to the batteries. And why is that? Well, a lead acid cell, a typical lead acid cell, fully charged is 2.2 volts, and it discharges down to about 1.75, and that varies on manufacturer. And if you take a 12 volt battery, it has 6 cells, a 48 volt system has 4 12 volt batteries, so you end up with charge to fully discharge range of 53 to 42. And then to actually fully charge the battery, you float the voltage a little bit higher, and that's where the 54.5 comes from. So you're floating the bus at the same voltage as the charging voltage, and that's an important point I'll talk to in a second here. But let me just go back to this low voltage issue. Keep in mind that if your 12 volt is really running 13.6 and your 48 volts running really 54.5, you actually have 68 volts potential between two terminals. And again, that's why it would be unsafe to have a negative 48 and a positive 12 volt. Just continuing the whole 54 volt thing, why do we float it like that? That's not necessary, right? You could have, and in fact, originally telco didn't require this. Point here is that there's different ways of solving a problem, right? Initially, they actually had a separate charging circuit for the batteries. The power was actually 48 volts, and the equipment was getting 48 volts. And then they said, yeah, but if the charging circuit fails, I don't know that my battery plant is ready. The safest way to do backup batteries, the whole point of the backup batteries is they're there for backup. They're supposed to be there ready for you when you need them. It's a safety device. And so the safest way to do that is to basically have them on the same piece of copper, right? Your equipment and batteries are on the same piece of copper. There's nothing between them, maybe a breaker, right? But certainly no active components. So it's easier to just float all the equipment at the same voltage, but then that means the equipment has to be able to live in a varied voltage environment versus a tightly regulated 48 volt environment. It's going to have to float along with the batteries, but that does make it a lot more reliable. So that's the point here. And so the OCP recognizes that. The OCP isn't trying to tell you to use one battery or another, so they're saying, yeah, we know that. So the range that they actually ask for the equipment to handle is from 42 to 58 volts, and that's the reason why. Because someone may decide to use the OCP standard to develop a rack system with batteries, and the batteries are lead acid, batteries are charging off the same bus, and so the equipment would have to live in this environment. Next, talk a little bit about efficiency improvements. And again, this is just Ohm's law. You know, everyone knows this. You can run the numbers on this yourself. But just these graphs are interesting because it shows such a marked difference. And really, just follow Ohm's law. If your voltage is going up 4 times, then current drops 4 times. And then resistance, if you're doing equivalence resistance, that's 16 times. And that's not exactly right, because then if you go to the NEC ratings and capacity ratings for cables, they also have temperature factors involved in them. So you end up roughly, maybe 9 or 10 time difference in the cable size. But that's substantial. So I want to point out here, really 48 volts is always more efficient. It really starts to hurt above that 15 kilowatt number that we mentioned, right? So that's kind of there towards the left of the graph. 48 volt just kind of continues. I mean, there's a slope down in the 48 volt, but because, to try to show both on the graph, the 12 volt just drops so dramatically, the 48 volts not dropping nearly as much in efficiency, even you go up to the 36 kilowatt load. That's kind of like the max target for OCP. Another interesting graph looking at that, this is Busbar cross-sectional area. And again, we're looking at this graph from 9 kilowatts to 36 kilowatts. The orange line is the 48 volt, blue line is a 12 volt. And one of the things I want to point out here is that the biggest bus bar that you would use at 36 kilowatts in 48 volt is actually the smallest one that we're starting with at 9 kilowatts for 12 volt. Right, so that's 250 millimeter squared line. And 36 to 9, that's 4, right? So again, that's your factor 4. I mean, again, simple math, but when you see it in a graph like that, you're going, so wait a minute, I could do 36 kilowatts with 48 volts, same copper, or only 9 with 12 volts, or if I really wanted 36 kilowatts with 12 volts, my copper's gone up to, whatever that is, 2,500. I mean, it's 10 times more copper. So that's pretty painful. And again, we think that, we can probably make it work in the 10, 12, 15 kilowatt range for 12 volt. Once you get above 15 kilowatt range, you really should consider 48 volt. This is important. We think it's actually more important for the manufacturers of the equipment, right, the servers and everything, to consider this, because you may be focused on your one-use server, and you go, yeah, well, so we're using more power. Well, we're going to have to manage all that power in a rack, right? So your additional power may be, oh, yeah, we're using 50% more power, but that's not too bad. And for one product, it's not. You get 10 or 20 of these in a rack, it becomes very significant. And so, this is where, it's logical for the switch, server, CPU manufacturers to consider, 48 volt, receiving 48 volt for their equipment and then handling the voltages internally. Next step, overall data center efficiency. And this goes to the point that I was just talking about, what we're doing, right? So obviously, we've got utility powers. That's where we're getting the power. We're going to do something to that power, something magic, something quick. And then we're going to power our chips, which are all DC. They're all, sub 5 volt, range today. And so what is this magic thing that we're doing to the power here in the middle? Well, it's actually fairly elaborate. And this is just this is actually a very simplified diagram of a typical data center. But it goes to the point that there's a lot of stuff here, right? It's not a simple matter to take high voltage AC and give it to chips at a low voltage DC range. So obviously you have utility towers, primary transformers, and a typical traditional AC to DC power path, right? That's the line on top. You got a generator, you got a UPS, you got batteries, secondary transformers, secondary panels, PDUs, AC to 12 volt rectifier in the current design, then you got your payloads, and on the cards you're converting your 12 volt down to your actual chip level voltages, 3.3, 1.8, whatever it is, and then the chip finally gets its power. Now, you could say, okay, we'll do 48 volt, our equipment's still 12 volts, so what we're gonna do, keep the line exactly the same, so here where I'm saying only replace the 12 volt with 48 volt, I've actually added a step, right? That little box in orange or in yellow where we're doing we got 48 volt to the rack, and now at our equipment, we're just gonna do a quick conversion down to 12, and then 12 to the points of load, and move on from that. That's actually, so if you look at both of these graphs, each step obviously has a percentage efficiency loss, right? And sometimes they're not big, 1%, 2%, but they add up. You got 10 or more steps here. Each one of them even at 1%, substantial loss in efficiency and loss of energy. And you do this 12 volt to 48 to 12 volt conversion, you've got an additional loss. Now, there's still an advantage to doing this. Certainly, as you're transitioning from 12 volt to 48 volt, it's logical to do this in some applications, but this shouldn't be the overall target. You certainly have an advantage of having the entire rack be 48 volt and doing conversion at the equipment. But it's not like the final goal that we're trying to get to. So looking at the same arrangement, just copy the line on top is the exact same one as from the previous slide. And just for comparison, you're saying, well, what if we try to optimize the entire AC to DC power path? What if we did only one primary transformer, right? But instead of being 480, it's maybe a 415 transformer. 415, 4-wire transformer, you get 240 right on the output. You don't need a secondary transformer, so got rid of that. What if we put the batteries in the rack, right? It's actually where you need them. Got rid of the UPS, right? That's a big savings. What if the equipment itself, the cards and the shelves, take the 48 volt in and go directly from 48 to the point of load. Go to 48 to 1.8 or 3.3, whatever your usage is, right? Now you're actually looking at a big improvement in overall efficiency. You have a big improvement already with just using 48 volt, but if you follow this, this adds maybe an additional 10% improvement in energy savings to the whole system because you've optimized the entire data center. And this is kind of like, we're looking at kind of a macro and micro thing. Sure, there's advantages at the rack. There's also advantages at the data center, right? If you really think about it from all the way from the utility tower coming in, there's definitely an advantage of optimizing the whole flow of power, ending with 48 volt at the equipment. Now, when you do this, when you reduce your secondary panels on the other stuff, now you're actually creating short circuit current rating issues, which you might want to look at. We looked at that in our design, and I'll talk about a little bit more downstream. But again, the potential savings is real. It's, like I said, easily 10%. We can argue that it's more than that. And it's worth considering as you're designing the next generation data centers. Okay, now I want to talk a little bit about the actual design we came up with. We wanted obviously to play well with the Open Rack version 2.1 standard. It's a nice standard. It's not too detailed, but it gives you just enough stuff so that equipment can work together. Here we have an example. This is the rack we didn't manufacture. That's a version 2 rack from a manufacturer. Our equipment just bolts into it. And what you see there is our power supply on top and battery shelves on the bottom. We wanted to have high power density, 36 kilowatts, support both balanced 3-phase and single phase, and then have batteries in the rack. Because again, this is part of the overall system efficiency. Put batteries in the rack, you can eliminate the entire UPS. UPS is gone. You have the generator, but we're backing up the power until the generator kicks in, so there's no UPS. We're starting with our Telco Grade 48 volt power module. And good thing about Huawei is we make these by the millions. Very efficient power, dozens of patents connected to it, 98.1% efficiency, highest in the industry. Very high power density. Today we have 3,000 watt unit, 4,500 watt is basically being released, as we speak. So very high, and they're plug-in compatible. You could use one, you could use both in the same shelf. So it's a very powerful starting building block. And again, this came from our telco experience. Then we go to a shelf. So we decided to take 9 of these 4.5 kilowatt units, put them in a shelf in arrangement ABC, 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 so they can work very well in a 3-phase environment. They connect to the OCP connector that's defined by the standard. Like I said, we're wiring these units ABC, 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 so that you can hook up 3 single-phase lines individually or put a jumper between the returns basically on the 3 lines and make that your neutral and work in 3-phase world. Perfectly balanced in 3-phase and also perfectly happy to work in a single-phase environment. And this just shows more details on how that's wired internally, again with a jumper. In this case, it's showing the jumper going to a 3-phase transformer. Doing it this way, we have the option to use a single plug, just one big plug, not a whole bunch of little individual plugs going to a PDU. But you don't need a PDU, right? Just go straight to like a big connector junction box, maybe with one big breaker on it. If you choose to, of course, you can also choose to run 3 individual lines to the unit. In order to deal with short circuit current rating, we also added fuses on the shelf. Again, this is to help reduce all those other pieces of equipment in the data center. So we have current limiting fuses in the shelf to help maintain a high SECR rating for the shelf. This is important so that it can survive in these more optimized environments. So this shows more details on that arrangement. You could have a 100,000 amp design, and then go through our fuses, the current limiting fuses, reduces that to 700 amps, and then our internal fuses, of course, protect the equipment internally. But this is the way to coordinate the current protection as you go through the product. So again, this helps be that important part of the more optimized data center. Next thing we did, batteries, right? So you're going to put batteries in the shelf. You can't put just lead acid batteries. They're too big or too heavy. When lead acid batteries leak, you get acid everywhere. That's pretty dangerous. Went with lithium batteries. And so we developed this one shelf, single 1 OU shelf with 3 modules, so 7.5 kilowatt battery shelf with a blind mate connector, so you can add these shelves as you need them, right? You don't have to, buy a large monolithic unit if you don't have your rack fully configured yet. Buy as many battery units as you need, or if you want more backup time, this is designed for 2 minutes. If you want 5 minutes, you can use some more of these shelves. Because it's a blind mate connector, you can connect this with the equipment active. You don't have to go in the hot aisle. You don't have to disrupt your airflow or anything. So it's plug and play in the hot aisle, with the equipment hot. Now, we selected lithium iron phosphate for our chemistry. Another very popular chemistry is nickel manganese cobalt. But we've done designs with that. So I don't want to make this black and white, that one's great and the other one is terrible. But there are definitely, in a data center environment, there are definitely some advantages to using the iron phosphate chemistry. The nickel cobalt is definitely higher energy density. That's why you might want to consider it. But during damage tests, right, it certainly does not survive as well as the iron phosphate chemistry. And to go to those details, and this is testing that Sony did. The iron chemistry pictures are on top, very, very boring pictures. Basically, nothing happens. The nickel cobalt pictures on the bottom. You have fires, explosions, pretty dramatic stuff. generally, I think we want to avoid that in data centers. Another test is a burn test. Again, the iron phosphate is a pretty controlled event, whereas the nickel cobalt, what we're trying to say there is the cell is actually gone from the picture. It actually blew up and flew out of the frame of the picture, whereas the iron phosphate's still there. So overall, we think that iron phosphate is the safer chemistry. It's a best balance of safety and capacity and cost and everything that we'd look for in a data center. As we're doing this design, one of the things that we looked at is how is this going to survive, thermally, right? But as we're analyzing this, we realized that the batteries only function for 2 minutes a few times a year, 6 times a year, something like that. We don't need to manage their heat in a constant state way. It's really a transient problem. So this is an actual test result. We're starting at 45 degrees C, so you're already really, really hot in your data center, right? You're at 45 degrees C. We go through the discharge, rapid heat up of the batteries, obviously, because they're dumping all their energy. They've got 2 minutes to dump all their energy, right? And then we stop at 120 seconds, 2 minutes, right? We stop the discharge, and then the batteries continue to heat up, right? Because they built up all this energy, and now the heat is actually conducting its way out from the center of the cells out to the environment. And then it takes a while for them to go through the cool down. But this actually is all within spec, right? We go up to 58 degrees. Again, remember, we're starting at 45. That's already worst case scenario. We go up to 58 degrees, and then we cool off from there. So that actually works perfectly well within the operating parameters for the batteries. We also looked at the full shelf, how it functions in the as related to other pieces of equipment. We don't want that 58 degrees to heat up other equipment. However, again, it's a transient problem. It only happens for 2 minutes. So what we notice happens after you do this, it heats up really, really fast. The process stops, right? You're on generator now. Batteries are not going into charge mode. The actual soak, the heat soaked into the entire environment was about 1 degree. So really nothing to worry about. Right? Even though the batteries themselves get very hot because it's a transient problem, you only see about 1 degree effect on the whole system. Finally, just talk about control. So there's a lot of ways to do batteries. We picked basically what we consider the safest way to do this. We have both a battery management system and a DC-to-DC converter in each battery module. They're self-contained, they're independent. We're not depending on some controller someplace else telling the battery what to do. The batteries are managing themselves. The battery management system has temperature probes all over the place. They know the temperatures of the cells. Anything goes out of range, they manage that. And then the DC-to-DC converter is also very important. It allows us to use basically any sort of bank of batteries that we're looking for, where the cell voltage may add up to 60 volts or 70 volts, really doesn't matter, because we are using the DC-to-DC converter to control the output to exactly whatever we set it to, which in this case is like 52 volts. And we're doing that because when we lose AC power, it was at 54, we want to see that drop of voltage until it reaches 52, and they say, hey, we're out of power, batteries have to go into discharge mode. So having that 2-volt difference allows us the time to see the event happen and then go into discharge mode. But the DC-to-DC converter will then hold 52 volts regardless of what the voltage in the batteries is doing. So that makes it a very safe output for the equipment, right? You don't have to worry about voltage spikes or anything coming through our system because we have a DC-to-DC converter. Finally, the whole system comes together with our communication module. We have, again, same kind of design. We have the power supply on top. In this case, we're showing 4 of these battery shelves on the bottom. You could have 2, you could have 10. It's up to you, however much backup battery power you need. And then it all goes to our controller. The controller can communicate to the outside world through SNMP web interface. And I know that's one of the things that's kind of an open topic in the OCP, what is going to be the management in the future. But I think we're all kind of headed to SNMP. It's all IP-based. Everything works with IP. So it's a real simple way to control it. And you could control the system from the office next door or across the world because it's all IP-based. It makes it very simple to control. So that was what we had. I know I just Just finished on time. So we have a little time of questions. If we run out of time here, we've got a booth, C20, on the floor. We'll be there the rest of the day. Please feel free to come and talk to us, and glad to talk to you, share more information, whatever you need. Thank you. Yes.
Can you come over to the microphone? Where's the mirror? Oh, there you are. Sorry. Why don't you go ahead and start getting set up? You can answer questions while.
Yeah, sure.
Set up.
Yeah, I have a question about your BBU. So you're using an LFP versus NMC cells. How do you account for the difference in the total number of cells to make up for the lower voltage and lower capacity? You feel it's worth giving up that much rack space?
Yeah, it depends on, so the way to the analysis is, if all you're doing is everything's equal, you're either putting one cell or the other cell in your enclosure, then yeah, the NMC is going to be more space efficient. But you haven't accounted for their failure mode, which is kind of dramatic. If you build an enclosure, which we looked at this analysis, right, that's actually strong enough and has the right features mechanically and thermally and everything to protect those NMC batteries or protect the rest of the world from the NMC battery type of failure, you find that the difference in density is much less than what it would appear, right? There's still a little bit of advantage, but it's not nearly as much as you would think. So, but again, with our DC to DC converter, we can put more cells in there. In fact, we've got 64 cells in there. I think it works out to be 60 some odd volts that, when they're fully charged. We can't dump that on the bus, right? That's why we have the DC to DC converter. So that's actually what makes them work with very good density. 7.5 kilowatts is actually very decent density for the shelf, but without having, like I said, the limitations that we would get from the NMC cells.
Time?
All right.
Go ahead.
Okay, thank you.
Yes.
Hi, Brian Donsick of PowerX. Yep, by all means, yeah, you gotta talk and walk here. Hey, I was just curious. You had mentioned that you would expect the, for the kind of the full, low state of charge cycling to occur. What do you say, on the order of 4 or 5 times a year? And I'm just curious, is that due to anticipation of actual, hold-up requirements for the system, or is that programmed into the algorithm for discharge for the health and life of the cells, especially with the difference between.
Okay, so there's actually two things.
Little
so
sensitive.
it's designed to work actual events, right, where we lost AC power and we're waiting for the generator to kick in. That's what it's designed for, and that's you could make the case 4, 6, 12 times per year, right? Yeah, exactly. If you've got 12 times, you've got other problems. You can talk to the electric company. But then beyond that, you actually do have to maintain your cells. So that's all done internally, right? I'm not even counting that.
Sure.
So you have to do top up, check your voltages, but the battery management system's taking care of that. So what I was talking about was really just actual events, not the natural topping up, maintaining the battery health cycles that happen. That happens a lot more often. But we're never going to a full discharge.
Sure. Okay, because the culmination of all those things are really what's going to impact the actual battery life cycle, life viability, state of charge over time, lifetime stuff. So
yeah, no, and that's actually very important. And to answer your question, 7.5 kilowatts, you're saying, well, yeah, but I could see something going higher capacity. In fact, the shelf is much higher capacity than that. 7.5 kilowatts is after 5 or 6 years of life. That's kind of our promise on the product. So it's actually end-of-life capacity. If you use it today, it's probably closer to 9 kilowatts. I mean, out of the box. So it's actually really comparable to nickel cobalt.
Okay, thank you very much.
All right, thanks. Sorry.
Yeah, no problem. Thanks a lot, Pedro.